AI is changing everything so fast, isn't it? I mean, look at what's happening with creative stuff. Images, text, you name it. We've even seen AI making some pretty cool short musical pieces. But,
Mhm.
you know,
Mm.
for a lot of people, the real holy grail has always been long-form music generation.
Absolutely.
Like actually crafting whole songs with lyrics, vocals, and instruments all working together. It felt almost impossible not that long ago.
Yeah, it really did. And while there have been some really impressive proprietary systems that have come out, the problem is they've mostly been these kind of closed off black boxes.
Yeah.
Hard to understand how they work, hard to build on them. And that's really why I think what we're diving into today is going to be so interesting for everyone listening.
Exactly. Today, we are taking a deep dive into YuE, which is written, uh, and it's this new family of open foundation models that are specifically designed to tackle this challenge, this long-form music generation, and particularly the process of turning lyrics into full-blown songs.
Yeah.
And what's amazing is that these models can actually generate music up to 5 minutes long. And they can do it while keeping the lyrics coherent, the structure of the song makes sense,
Yeah.
and even creating these really engaging vocal melodies with fitting instrumentation. It's crazy.
Yeah, and it's the open source nature of you that is, I think, really transformative in this case, right?
Yeah.
Unlike those proprietary systems we were just talking about, this just opens up the doors for so many more people. It means wider access. It means researchers can really dig in and replicate and build on the findings. And I think it opens up the potential for community-driven innovation in a way that we just haven't seen before.
Huge. Yeah. All right. So let's get into the nitty-gritty for you, the listener. We're going to explore exactly how YuE works, what's going on under the hood, the architecture, the key research findings, what methods they use, the strengths, the limitations, and even what the future might hold for this tech. And we're going to be pulling all this straight from the research paper.
Yeah.
So you can be sure that you are getting a really clear and accurate understanding of this super exciting development. So where do we start in grasping how you actually pulls this off?
Well, I think the core of it is this really interesting architecture. It's a two-stage process.
Okay.
So the first stage is called music language modeling, which they shorten to MLM. And then the second stage is called residual modeling. So think of it as sort of a two-part approach.
Okay.
The first part establishes like the core musical meaning and structure, and then the second part goes in and refines the sort of finer sonic details.
I got it. So stage one, music language modeling. What's the main objective here? What are they trying to do?
So the main goal in this initial stage is to generate what are called, and this is a bit of jargon, but semantically rich audio tokens.
Okay.
And so for our listeners, you can think of these as like the fundamental musical building blocks, things like notes, chords, rhythms, but they're represented in a way that captures their core meaning to the AI. And to do this, they've developed this really cool technique called Track-Decoupled Next Token Prediction, or dual NTP for short.
Track-Decoupled. That sounds like it could be pretty powerful. What does that actually involve?
Yeah. So basically, when the model is learning, it actually separates the audio into two distinct streams.
Okay.
One focuses on the vocals, and the other focuses on the instrumental accompaniment. And the thinking here, for you, the listener, is that music is often this really complex, overlapping, like a mixture of sounds. They call it dense mixture signals in the paper.
Makes sense.
Right. So by processing the vocals and the instruments separately, the model can sort of learn their individual patterns more clearly without one kind of getting in the way of the other.
Yeah, that makes a lot of sense. It's like when you're listening to a song and you try to isolate an instrument and just hear what it's doing.
Yeah, exactly.
So what did the researchers find when they started doing this separate processing? What kind of effects did it have on the training?
So a couple of interesting things they found. First, this dual NTP technique led to something called a lower training loss,
Okay.
which basically means that the model learned more efficiently.
Got it.
But maybe even more importantly, it led to much more robust lyrical adherence. So basically, even in musical styles where the arrangement is really dense or complicated,
Yeah.
it seems that by really focusing in on that vocal track, the model is able to more reliably connect the words to the sung melody, which is obviously crucial for lyrics to song generation.
That makes a lot of sense, and it's a really big deal for this kind of tech.
Mm-hmm.
What else is going on in this first stage of UA?
So another really key technique they use is called structural progressive conditioning, or COTE.
QT. Okay.
And this is all about ensuring that the generated song actually have a logical structure and that the lyrics are properly aligned throughout the whole piece, which is really important for that long-form coherence that we were talking about earlier.
Yeah, absolutely. So how does that work in practice? It sounds like this is directly addressing the challenges of creating longer musical pieces.
Exactly. So what they do is they segment the song into its kind of natural parts, the intro, the verse, the chorus, the bridge, the outro, all those sections.
Right.
And then the model generates these sections in sequence, with each part sort of being influenced by what came before it.
Okay.
So it's this progressive approach, and it really helps to maintain that lyrical alignment and make sure that the overall structure of the song feels coherent and intentional, even over these longer durations. It's like, building a story step by step.
So it's not just like throwing musical phrases out there and hoping they fit together.
Exactly. It's about understanding the overall architecture of the song. And then finally, in the first stage, they also incorporate a redesigned approach to something called music in context learning, or ICL for short. And this is really where YuE starts to show off some of its more flexible capabilities.
In context learning. So we've seen that pop up in other AI fields, but how does it apply to music generation here?
So their enhanced ICL enables some really cool things, like versatile style transfer.
Okay.
So imagine you have, let's say, an instrumental track in the style of, I don't know, Japanese city pop,
Right.
and you want to generate an English rap song, but you want it to use that same instrumental feel. You can actually do that. It can transfer the stylistic elements from one musical piece to another, even across different languages and genres.
That's incredible. So it's learning like the underlying, I don't know, feel or vibe of the music.
Yeah, in a way, yeah. And this redesigned ICL also supports bidirectional generation, which is really cool.
Okay.
So instead of just continuing a musical idea, it can also generate music that precedes a given segment, so it gives you even more creative control. And they can even use both the vocal and instrumental tracks of an existing song as a starting point for generating something new that has a similar feel.
Wow. The creative possibilities are already pretty mind-blowing, and that's just stage one. So what happens in stage two, this residual modeling phase?
So stage 2 is all about refining the output from that first stage. So the audio tokens that MoLem generates are, in a sense, kind of like a rough draft, right?
Okay.
So residual modeling takes those rough tokens and predicts finer, more detailed residual tokens. It's like taking that rough sketch and adding layers of detail and polish.
So it's basically taking that like musical skeleton from stage one and then filling it in and making it sound like a finished, polished piece of music.
Exactly. And it does this using an autoregressive approach across different audio codebooks.
Okay.
So it's basically predicting and adding these small pieces of information step by step to make the final audio output sound much higher fidelity, much more like something you'd actually want to listen to.
So for our listeners, how does you actually represent music in the first place? Like what kind of tokens are we talking about here?
Right, so they use something called a hybrid tokenization scheme, which means they're combining both semantic features, which is like the meaning and structure inherent in the music, and acoustic features, which are the actual sound characteristics.
Okay.
And to do this, they primarily use neural codec tokenizers, particularly one called X-codec, which they found to be really effective across a wide range of musical styles.
So X-codec is like the key to translating that raw audio into these tokens that you can then work with.
Exactly. And then to produce that final high-fidelity audio, the thing that you would actually listen to, they integrate a lightweight vocoder.
Okay.
So this vocoder takes the tokenized output and basically upsamples it from a lower sampling rate, 16 kilohertz, to the standard high-fidelity rate of 44.1 kilohertz.
So two-stage process, some really innovative techniques in each stage, a clever way of representing the music, and then that final step to ensure good audio quality. That's a pretty clear picture of the architecture. So what about the results? What were the key insights from their experiments? What really stood out?
I think the most striking finding, the one that really jumped out at me, is that YuE's performance in terms of both the musicality, how enjoyable the music is, and the naturalness and agility of the vocals, it matches or even surpasses some of the best proprietary systems that have been around for a while.
Wow. Okay.
And I think it's really important to emphasize, remember, YuE's is open source,
Yeah.
which makes this even more of an achievement.
That's huge, right? Like open source technology achieving, if not exceeding, the capabilities of these closed-off systems. That's really something. So what other significant things came out of these experiments?
Yeah, another thing they really highlighted was YuE's ability to consistently generate coherent music for durations up to 5 minutes long.
Okay.
Now, that might not sound like a lot, but for AI-generated music, that's actually a really long time.
It is.
Maintaining coherence over that length of time is a big technical challenge. And they did a bunch of comparisons with those proprietary systems focusing specifically on the musicality, like how much listeners actually enjoy the music, the quality and expressiveness of the vocals, and the overall emotional impact of the generated pieces.
And in those head-to-head comparisons, how did you fare?
They found that the 7 billion parameter version of YuE, which is a fairly large model, but not enormous by today's standards, was actually able to produce some remarkably advanced vocal techniques and performances that sounded really spontaneous. They used the term vocal agility, which I think is really apt. It wasn't that kind of flat robotic singing we might have heard from AI in the past.
Wow. So AI generating vocals that actually sound spontaneous, you kind of have to hear it to believe it, I imagine.
Yeah, you really do. And this capability wasn't limited to just one genre. They found that YuE is quite versatile. It can handle different musical styles, different languages, different vocal techniques, and it could do it while maintaining that structural coherence we talked about, even in those longer pieces.
And what about languages other than English? Because that's often a stumbling block for these models, right?
Right, so they did specifically look at multilingual applications, and they found that by fine-tuning YuE, they could significantly improve its ability to handle other languages, like generating songs with Japanese lyrics. And even more impressively, they demonstrated cross-lingual style transfer.
Okay.
So, for example, taking the instrumental track of a Japanese city pop song and generating an English rap over it, which suggests that it's not just about translating words, it's actually understanding something deeper about the musical context.
That's amazing. That's going beyond just like translation and into like musical understanding.
Yeah, exactly.
Are there any other findings that really surprised you?
Yeah, there was one that was really interesting. They found that the representations that YuE learns during its training, the way it understands music, were actually not just useful for generating music.
Okay.
They actually performed really well on music understanding tasks. They tested this on a benchmark called Marblelet, and in some cases, YuE's representations actually matched or even outperformed state-of-the-art methods specifically designed for music understanding.
So it's not just that it can create music. It's that it actually understands music on a deeper level.
Exactly. It suggests that it's not just mimicking patterns, but actually developing a more generalizable understanding of music itself.
That's fascinating. All right, so we've talked about the architecture and the key experimental results, but let's go back to those really novel techniques they introduced. What are like the big takeaways there?
Yeah, so I think for sure the dual NTP technique, the way they decouple the vocal and instrumental tracks for prediction, that seems really crucial for managing the complexity of music and for improving that lyrical integration.
It seems like, yeah, addressing that polyphony, that overlapping sound at the token level, that's a really big deal. And then there's the structural progressive conditioning, the COT, that step-by-step generation based on the structure of the song. That seems key for that long-range coherence we keep talking about.
Yeah, it's like having a roadmap for the song before you start filling in the musical details.
Oh, yeah, exactly.
And I think we shouldn't overlook the multitask and multi-phase pre-training recipe, like that really extensive training on a massive data set with different objectives at different stages that undoubtedly plays a big role in enabling you to learn these really complex musical patterns.
Yeah.
And then, of course, that redesigned in-context learning is really what unlocks a lot of those creative possibilities, that style transfer, that bidirectional generation. That's super cool.
So big picture, what would you say are the major strengths of you and this research effort as a whole? Like what really makes it stand out?
So first and foremost, it's open source availability.
Yeah.
Under the Apache 2.0 license. I mean, that cannot be overstated. Anyone can use it, build upon it, even potentially monetize it, as long as they provide attribution. That is a huge boost for accessibility and for future innovation. Then there's the long-form generation capability. Being able to create these complete, cohesive songs, that's a significant step forward. The quality of the generated music itself is really impressive, matching or exceeding proprietary systems in terms of musicality and vocal agility.
Yeah, and it's doing all this with these novel technical contributions, the dual NTP, the SUT that we talked about,
Yeah.
which are real advances for the field.
Yeah, for sure. And then the fact that it's built on the Lam 2 architecture suggests that there's good potential for scaling this even further. And then we can't forget that strong performance on those music understanding benchmarks. It really points to a deeper comprehension of musical concepts. And I think it's also worth noting that the way they model vocals and instruments jointly in a single process, that's actually more efficient and helps maintain coherence in the output.
All right. Lots of positives here. But of course, no research is without its limitations. What are some of the things that the researchers themselves say still need more work?
Yeah. They're pretty upfront about where they want to go next. They specifically mention that they want to focus on enhancing the acoustic fidelity of the music, so making it sound even more realistic and polished,
Right.
and also giving users more nuanced control over the emotional content that's expressed in the music. And these are, ongoing challenges in the field.
Yeah, absolutely. And what are some of the other just like inherent difficulties of long form music generation that they pointed out?
Yeah, so I mean, creating these full-length songs, it's inherently complex. You're dealing with these temporal structures that unfold over minutes, the intricate interplay of all these instruments and vocals, the way lyrics are stretched and shaped when they're sung, and then just the relative lack of really large, high-quality data sets that pair lyrics and vocals and accompaniment perfectly.
Right. And what about those in context learning capabilities? Were there any drawbacks or limitations there?
Yeah, so the current in-context learning implementation still requires you to have text transcripts, even when you're using reference audio for style transfer, which can be kind of a pain if you only have, like, the audio and not the lyrics.
Yeah.
And the music continuation feature is currently unidirectional, so it can only generate what follows a given segment, not what might have come before.
Okay.
And then there's also the potential for what they call entanglement during continuation, which basically means the model might replicate the reference audio a little too closely, which could raise copyright issues
Yeah, that's an important consideration.
and limit the originality of the output.
Absolutely.
Yeah.
What about just the practicalities? Like what kind of resources do you need to run you?
Yeah, so the computational demands are not insignificant. They do mention needing a fairly substantial amount of GPU memory, which might make it inaccessible to some users without, pretty specialized hardware.
Right.
And the time it actually takes to generate music can also be quite long, depending on the length of the song and the resources you have available.
So it's not something you're just going to run on your laptop in a few seconds, at least not yet.
Probably not, no. And then it's important for listeners to know that the Apache 2.0 license does come with disclaimers, so users are still responsible for making sure that what they create is original and doesn't infringe on copyright.
Right.
And while the researchers believe that YuE largely avoids directly memorizing the training data, it's still something to be aware of. And then, of course, the final audio quality is dependent on the quality of the X codec and the vocoder that are being used.
It's good that they're transparent about these limitations. And one thing I thought was really interesting was that they actually included a section in the paper about approaches they tried that didn't work.
Oh, yeah, the unsuccessful attempts section.
Yeah.
I thought that was really cool.
I think that's so valuable for the research community.
Yeah.
Seeing not just what worked, but what didn't work
Absolutely.
gives you so much context for their final design.
Yeah.
Yeah. All right. So lastly, let's talk about how they actually did the research, how they evaluated Yuzi's performance. What did that involve?
Well, the scale of the training was impressive. They trained it on trillions of music data tokens, and as we mentioned, they used that multitask, multi-phase pre-training strategy.
Okay.
And then for evaluation, they used a combination of subjective human evaluation, so actual people listening to the music and giving feedback,
Okay.
and objective automatic metrics, things like KL divergence and FAD.
So they look at both the hard numbers and the actual listening experience.
Exactly. And they even investigated how well those automatic metrics actually correlated with what human listeners preferred. And they found that some commonly used metrics, like something called CLAP score, didn't align that well with human judgment. While others, like Clam MP3 score and vocal range, were more consistent with human preferences, which I think highlights this ongoing challenge of figuring out how to reliably assess the quality of music automatically. They also compared different sizes of the YuE model, benchmarked it against those proprietary systems we talked about, and probably did a bunch of ablation studies where they removed different components to see how it affected performance.
Okay. Well, we've covered a lot of ground here, I think. So what would you say is the big takeaway message for our listeners? What's the headline here?
I think the key takeaway is that YuE represents a really significant step forward for open source AI music generation, especially in its ability to create these full-blown songs from lyrics. The level of performance is impressive, and its open source nature has huge potential for democratizing music creation.
Yeah, absolutely. And what are the main directions for future work? Where do things go from here?
So they specifically mention improving the acoustic fidelity even further, making it sound even more realistic, and giving users more control over the emotional expression in the music. And they even hinted at some potential applications in areas like music education and therapy.
Really interesting stuff. And, they actually have a public to-do list for the project,
Yeah.
and they list some really specific things they're working on. Do you want to touch on some of that?
Oh, yeah, for sure. I mean, it shows how active this development is. They're planning on adding things like example code for controlling the tempo or BPM, support for stem generation, so you can isolate the individual instrument tracks, integration with llama.cpp, which would make it more efficient on different hardware, tensor parallelism to speed up training and inference,
Yeah.
making it available on Hugging Face spaces, support for things like VLLM and Sklang, improving the user interface, adding seeding for reproducibility, customizable repetition penalties. It's a long list.
Wow, sounds like a really dynamic, forward-looking project.
Yeah.
So as we wrap up this deep dive, what's the big question that YuE raises for you? What should listeners be thinking about as they go forward from here?
I think the emergence of these powerful open source AI tools like YuE really forces us to confront the potential impact on the music industry and on creative practices more broadly. It's such an exciting time. On the one hand, it opens up incredible opportunities for more people to express themselves musically, but it also raises these really complex questions about creativity, about ownership, and about the evolving role of AI in the arts. It really challenges us to think deeply about what it means to be a creator in this rapidly changing world, and maybe even to explore YuE and see what we can do with it ourselves.